If I were to relate this reaction to the activity I mentioned where we have two people with paper wads going back and forth to one another, at the start of the reaction, the start of the example, one person would have all the paper wads on his or her side. They would be throwing the one paper ball at a time to the other side. The other person would then receive the paper balls. He or she would be able to throw two paper balls at the same time back to the other side. This would continue back and forth until eventually the number of paper wads on either side isn't changing over time. So let's say this person has 12 paper balls on his side and the other person has 24. No matter what happens, the rate of the reaction, those are consistent number of paper balls that are not changing. So the concentration remains the same, even though it's not the same number of paper balls on either side. So the concentration is decreasing for the forward reaction, increasing for the reverse reaction, until eventually there's no real change in concentration for either side. This is a graph representing the same reaction, but instead of concentration on the y-axis, we have the rate of the reaction on the y-axis. So to start, the rate of the forward reaction is higher because we only have this reactant. We don't have any products, or which would be reactants for the reverse reaction. Over time, the rate decreases for the forward reaction because the concentration of N2O4 is decreasing. So as the concentration decreases, the rate at which this reaction can occur is going to decrease. Whereas on the other side, the rate of the reaction is increasing because we're gaining product. As we increase the concentration of the product, which is the reactant of the reverse reaction, the reverse reaction rate will increase. Eventually, at this point, the rates of the forward reaction and the reverse reaction are the same. So the change in number of, or the change in balls being thrown basically is the same. That's the rate. So even though the concentrations are different for the reactants and products, the rate of the reaction remains the same, and that is what defines equilibrium. It's not that the concentrations are the same, they can be different, it's that the rate of the forward and reverse reaction are equal to each other, but the concentrations of reactants and products are not changing over time. So again, in this example, initially the system only contains N2O4. Eventually we're making NO2, so the rate of the reverse reaction does increase over time. So when the rate of the forward reaction again is greater than the rate of the reverse reaction, that means the forward reaction is occurring more. There's a net conversion of reactants to products. The reversal reaction is proceeding to the right. So if we have more concentration, the rate will be faster again. So in the beginning here, this rate is greater than this rate. So we have a net conversion to products. In this example, the system initially contains only products, NO2, and eventually we establish equilibrium. So here we start with our product, NO2. The concentration is decreasing, whereas the concentration of N2O, which is represented as the reactant in this equation, is increasing over time. And then eventually around here, we establish equilibrium again because the concentrations are not changing for both reactant that we started with, which is the product here, and product, which is listed as the reactant here in the equation. And again, for this initially having NO2, the rate of the reaction decreases over time, whereas the rate of the forward reaction is increasing over time as we produce N2O4. So when the rate of the reverse reaction, as we just saw, is greater than the rate of the forward reaction, there's a net conversion of products back into reactants. The reversal reaction is proceeding to the left. So we can say that if we have a higher concentration of products, that the reaction will proceed to the left. So you will hear that kind of vocabulary, proceed to the left or proceed to the right. It's basically proceeding towards products that are listed or reactants. They say left or right because technically, again, we have two reactions going on, and it's like all relative, what you'd refer to as reactants and products. So with this double equation here, usually we do refer to this as the product. Just keep in mind, because of the reversible reaction, that it can also be the reactant, which is kind of confusing. So once we have established equilibrium, there are no observable changes that occur, even though both the forward and reaction continue to take place. So with equilibrium, one moment in time, I mentioned like having 24 of one species and 12 paper rolls of another species. If we pause, maybe we end up with 13 and 25 at some point, but that's not really an observable change because it's not a significant change. So the forward and reverse reactions do continue to take place. The rate of the forward reaction is equal to the rate of the reverse reaction. Concentrations may not be the same of your species, but the change in concentration is 0 for both. In a closed system, equilibrium will be maintained because reactants and products aren't able to leave the system. In order for anything to change, something would have to be input. So true equilibrium must occur in a closed system because you don't want any outside interference, basically. The reactants and products can't leave the system, so concentrations and partial pressures remain constant, and new species that could influence the equilibrium cannot enter the system. So again, with reactants and products being able to leave the system, if I were able to remove some products, so some of the things that occur on the right side of the equation there, if I were to remove that product, then the forward reaction would occur at a stronger rate, or the reaction would proceed to the right. The volume of the system must also remain constant. This is really important in terms of gases. So if the volume changes, the partial pressure of gases would change, which would change the rate that the reaction would occur, and it would change the equilibrium of that reaction. And again, if the temperature does not change, the temperature must not change, because temperature is also going to affect reaction rates because it affects the average kinetic energy. So the number of successful collisions, either in the forward or reverse reaction, and the equilibrium position where equilibrium occurs. The equilibrium constant is represented by KEQ. So K is just constant and equilibrium is just represented by EQ. And we can basically represent KEQ through a stoichiometrically balanced chemical equation. So here we have lowercase letters representing coefficients, capital letters representing the species involved in the reaction. To basically figure out the equilibrium constant, we just have to take the concentration of products multiplied by one another to the power of their coefficient divided by the concentration of reactants to the power of their coefficients. The units for concentration, the value that would go in this, which today we won't be applying numbers, but later on in the unit we will. The unit will be in molarity, moles per liter. That's always what we use to represent concentration in this class. So if we want to find the equilibrium expression, which is represented by Kc, we would write the chemical equilibrium expression by taking the concentration of the reactants to the second power divided by the concentration of the products to the second power. Here we only have one product, divided by the concentration of the reactants to the power of 1, which we would not show in the equation. So our equilibrium expression for this equation would look like this. Okay. For this second example, it is going to be a little bit different because solids are always left out of the equilibrium expression, and we will get into why in a moment. So here in my equilibrium expression, I am not including nickel oxide or nickel solid because they are in the solid state. The only thing that's going to show in my equilibrium expression is CO2 gas and CO gas. In this case, both have coefficient of 1, so they will be to the first power, which again, we don't show 1 in the final answer. So our Kc would be equal to concentration of CO2, our product, divided by the concentration of carbon monoxide, our reactant. So it would look like this. The reason that solids are left out of the equilibrium expression, there's no good place for my face, is that the concentration of nickel 2 oxide essentially hasn't really changed, okay? So this is the initial volume of nickel oxide, and this is the final volume at equilibrium. So you see that the volume is reduced, but remember, concentration isn't volume, it's moles per liter. And because the density of nickel oxide for both of these are the same, because density is an intrinsic property that isn't determined by the amount that you have, both pieces have the same density, so they contain the same number of particles per unit volume, okay? So yes, the number of moles changes, but also the volume, liters, changes at the same rate. So the concentration overall doesn't really change. Weird to think about, I know. So solids are left out of the equilibrium expression for that reason. Try to move my face again. In this example, we have an aqueous solution, gaseous solution, and liquid. For this, another tip, liquids are also left out of the equilibrium expression. So I will not be including water in my equilibrium expression. In this case, I only have one product, Cl2. The concentration of chlorine gas will be raised to the second power, and then I would divide by the concentration of HCl to the fourth power times the concentration of O2 gas to the power of 1, which again, I don't show 1 in the final answer. So our equilibrium expression will be equal to this expression here. The reason liquids aren't included is basically very similar because density doesn't really change. That means that the concentration of water or any liquid doesn't really change. So if we were to remove or add a small amount of water, that would increase or decrease the number of moles of water, but it also increases or decreases the volume of water. So the concentration of H2O or any liquid really doesn't change, okay? So tips for writing equilibrium expression. We always include gases and aqueous species, but never include liquids or solids. So it's kind of like just rules to remember, like when we were doing net ionic equations. We don't break up solids, liquid, or gases. We only broke up aqueous solutions. Here we include gases and aqueous solutions, but we don't include liquids or solids because their density doesn't really actually change. We're changing the number of moles, but we also change the volume, so the concentration doesn't change for that reason. Okay, a few more minutes. Remember, we'll get through a few more slides. Here we have a reaction quotient, which describes the relative concentrations of products and reactants at any point in time. So remember, the equilibrium quotient, the K equilibrium, that is K, that is only at equilibrium. So anything with a K in front of it, whether it's Kc equilibrium expression or equilibrium constant, KEQ, that is only occurring at equilibrium. The reaction quotient, anything with a Q, can occur at any moment in time, before equilibrium, past equilibrium, things like that. So the expression is going to end up being the same. It's just the numbers that go in here would be different than they would be at equilibrium, potentially. When we are at equilibrium, when the system is at equilibrium, QC is equal to KC. So the value of QC and KC are the same. That means that QC is basically KC because it's the same expression, it's just occurring at equilibrium. So Q is for at any point in time during the reaction. K is specific only to equilibrium, okay? We're gonna wrap up notes there for today. I do want you to do some reading in your textbook, guided reading notes for homework, and I will see you in class tomorrow.